I want to do a little bit of consolidation of some of the basic steps in the processes that we do over and over again when we're working with continuous random variables. Um, and so one thing that makes this process complicated at the beginning is that most of the things that we want to do, finding probabilities, finding CDFs, finding expected values, those basic tasks have there's more than one way to do all of those things. And there's no clear, oh, this is the easiest way, that's the hardest way. It really depends on context. So the fact that there's multiple ways to get to the same answer is going to pretty quickly become an advantage, but right at the beginning, it seems to add complexity. So I want to try to sort that out in this video and the next one. Okay. So our starting place when we're working with continuous random variables is almost always with a PDF. So that, reminding ourselves, is the thing that's kind of the analog of the probability mass function for discrete random variables, except in this one big exception, which is that the PDF values, like when you graph it, the height of the PDF does not by itself give you a probability. Okay? And that's because with continuous random variables, we don't assign probabilities to individual outcomes. We have to assign them to ranges. So we do use the PDF to find probabilities, and that's what we're going to focus on in this particular video, but it's a little more complicated than it has been for the discrete random variables that we were working with at the beginning of the course. Okay. So the PDF is kind of the starting point, and it's sort of what defines random variables. So if a random variable is uniform or normal or exponential or has whatever shape, that random variable is its PDF. The PDF is the basic information, and we tend to get it in three basic forms. Okay, so sometimes we get the PDF in the form of an equation. Okay, and so I'm going to do the different forms for all the same PDF here. So an example of a PDF defined as an equation would be that little f sub x, and I'll write it out the kind of the nice way. It's a function of x, and it takes values 1/2 when x is between 0 and 2 and 0 otherwise. Okay, so this is one way we could get the information about a random variable. We could just be told that this is the PDF. Another way, an equivalent way to get the same information is with a picture. Okay, so for the same random variable, we could just be shown a picture here. We've got x on the x-axis and f of x on the y-axis here. And we could be told that this green function is our PDF. Okay, so that is the same information. And indeed, this is a function that takes the value 1/2 when x is between 0 and 1/2, and it's 0 everywhere else. So it really is just the same information, but displayed in a different way. The third way we get information is in words. So another way to give exactly the same information would just be to say random variable x is uniform on interval 0, 2. Okay, or we might even just write that x is distributed uniformly over the range 0, 2. And the important thing that I really want to emphasize here is that all three give the same information. Okay, and given any one of these starting points, sometimes it's helpful to add another one. So for example, if I'm given information about a PDF in the equation form, I often find it helpful, and I'll do a couple examples of this, to draw the picture anyway, because the picture just kind of helps me wrap my brain around what's going on. Um, Sometimes going from the words to the equation can also be helpful. Also, when you see an equation or a picture, if you can start recognizing the verbal descriptions, like every time you see a PDF that is just a flat line over some interval and zero everywhere else, if you can remind yourself that that's uniform, that's going to help you kind of leverage your intuition for working with these things. All right, so let's take those starting points and work on finding some probabilities. That's kind of the most basic thing that we do, is finding the probability of an event. And remembering once again that events cannot be a single outcome, they have to be ranges. So an example of an event would be the probability that X is less than 1/3. All right. And so here again, we have options. Okay. The first option is to find the area under the PDF corresponding to the event. Okay, so this option tends to work well with the PDF displayed as a picture. So this one that we're working with, which is 1/2 when X is between 0 and 2 and 0 everywhere else. It's my f of X here, right? And so if I want this probability that X is less than 1/3, what I do is I find the event that I'm interested in, 0 to 1/3. Okay, that's the probability that X is less than that. And what I am looking for is the area that has base 0, 1/3, and the height that is given by the PDF here. Okay, so what I'm looking for here is the area that is the base of 1/3 times the height of 1/2. Okay, and so 1/3 times 1/2 is just 1/6. Okay, so I'm just using very basic geometry here. What is the area of that rectangle? It's 1/6, and that is my answer. That is the probability that X is less than 1/3. Okay, so that's one option. Another option is to integrate PDF. Okay, so here we're taking the integral as S goes from 0 to, write that more neatly, here, 1/3 of the PDF of X, which we're reminding ourselves is 1/2, except we're at 0 and the integral of 0 will be 0, so we don't have to worry about that. And again, to do the integration, we ask ourselves, what is the function whose derivative is 1/2? That's not too hard to do. That is the function x over 2. We take its integral from 0 to 1/3, which just means that we substitute in first 1/3 and then 0 and take the difference. And so that is 1/6 minus 0 equals 1/6. Same as we got before. Okay, so I want to draw your attention here to how we get the event, like what event is the probability that we're looking for here into the calculation. If we're doing a picture, the event is telling us where on the x-axis we're finding the area above. Okay, so it's the base of the rectangle is what the event is here. If we're integrating, it's the limits of integration. Okay, so x between going from lower bound of 0 to upper bound of 1/3. All right. A third option here for finding the probability is use a formula for the CDF, okay? You can find formulas for the CDFs of all the kind of canonical random variables. So that would be the uniform, the normal, the exponential. Those are kind of the big three. And you can look those up in any book. We derived the CDF for the uniform random variable in one of the previous lessons. So sometimes that is the best choice. Let me actually put a little asterisk by the one thing I said a minute ago that wasn't exactly right. You could find formulas for the CDFs of the exponential and the uniform. The normal random variable famously does not have a nice closed form solution for the CDF, so we have to use a table. I'm going to talk about that in a minute. But in general, there is no problem with looking up the formula for the CDF and using it to calculate probabilities. Okay, so for this random variable that we're talking about, it is uniform on the range 0 to 2. And we, in one of the 7A lessons, derived the formula for the CDF of a uniform on the interval C to D. So for any uniform random variable, what we found is that the CDF, the probability that X is less than B, is equal to 0 when B is less than C. It's equal to B minus C over D minus C for B between C and D, and it's equal to 1 when B is greater than D. Okay, so that's what we derive. You can go back and look at that lesson. It's not a bad idea to actually go back and look at that lesson with fresh eyes. It's probably going to seem a lot more coherent now that you've been working with these things for a while. But just sort of checking your intuition, what this is saying is that when B is below the lower bound of the uniform, okay, when B is over here, the probability that the random variable is less than B is 0. It's not going to be there because C is the lowest possible value. Similarly, if B is greater than the upper bound, the probability that the random variable ends up less than something that is greater than that upper bound is 1. Okay, if we've got a B way out here, the probability that X ends up less than that B is 1. It's always going to be less than D. And for the for B values within the range of the uniform random variable, it's just the fraction of the distance, B minus C, from the lower bound to the upper bound of the event. Okay, so it's this expression. That's the general form of the CDF. To use it, all we have to do is plug in whatever values we have for C and D. And what we have here for the one that we're looking for is a random variable that is uniform on 0, 2. Okay, starts at 0, goes to 2, and has constant probability there. So putting that into the CDF values here, the CDF is 0 when B is less than 0. It's B minus 0, so that would be B over 2 minus 0, that would be 2 for B that's in between 0 and 2, and it is, don't need that extra 0, extra equal sign there. It is 1 for B greater than 2. Okay, that's the CDF. And then we just plug in the value that we care about here. We plug in 1/3 into the CDF. Where do I want to do that? I want to do that right down here. So fx of 1/3 equals, so 1/3 is between 0 and 2. I'm just going to plug in 1/3 for B. I get 1/3 over 2 equals 1/6. Yay, I'm getting that same answer all three different ways, okay? All right, so with these three different ways, a couple of things I wanna say. First of all, and this is the thing that is hard at the beginning, but it's gonna get easier really fast, is keeping straight the separate steps, okay? So once you find the area, you don't need to integrate, okay? Don't be mixing up the steps from these three separate processes here, okay? You can just do this, you can just take the area under the PDF, you can just integrate the PDF, or you can just use the CDF. It's not a bad idea to do it more than one way to check your answer, but again, keep the ways separate. So when you're finding the area, get to the area and you're done. When you're integrating the PDF, get to the definite integral and you're done. When you're using the CDF, plug in the parameters to get the right CDF, the one that fits the particular function you're working with, plug in your value, and again, you're done here. They're all valid options. They're all different ways of getting to the same answer. In terms of situations under which one option might be better than another, this business of looking at the area under the PDF, this is best, maybe, best very loosely or recommended here for simple PDFs given as pictures. Okay. So if the information you have about a random variable takes the form of some kind of picture where you can use basic geometry to find that area that you care about, this is a good way to do it. Okay. Using the CDF, that is probably best for the canonical random variables. Best, I would say, for the uniform, for the exponential that we're going to be talking a little bit about in the next set of lessons. It's also kind of best if you're just trying to get an answer. Integrating the PDF is best for learning. And that's why I've kind of encouraged you to use this process now. Not, as I've said, because I am really gung-ho on you guys practicing finding integrals all the time. I really don't care about that, but just this is the process that kind of lets you know at the deepest level what's going on here. Okay. And then the very last thing that you might do here is for a normal random variable. Okay. Going back, all of these probability finding strategies work well, except for the normal random variable. For the normal random variable, do not try to find the area under the PDF. Please do not try to integrate the PDF. The way you use the CDF, it doesn't look like this process, but the way that you are using it is what we did in lesson 7B. Okay, so you standardize and use a table. Okay, so you standardize it, you turn it into a standard, you turn the question you were asking, so x less than 1/3. For a normal random variable, you turn that into a question about the standard normal, that is one with mean 0 and variance 1, and then you can look up the probability in a table, or more realistically, you can use a computer package where you tell the computer the information that it needs to standardize and use its own internal table to give you those normal probabilities. Okay, so again, what we did here is we kind of started with the multiple starting points you can find yourself at when you're working with a continuous random variable, and came up with multiple ways to get to some endpoints, all of which that were the probability of an event. In the next video, I'll talk about the steps to follow for other questions that tend to arise. Finding probabilities, what we've just done here, is probably the most important thing that you do with a PDF. It's nice you're also asked to find the CDF by itself or to find expected values. So that's where we're going.